Well, welcome to the IAS Nobel lecture. I am Ken Biolok. I'm the director of the Center for Fundamental Physics here. And certainly I'm really excited to have this opportunity to introduce today's distinguished speaker, Professor KAJITA. Usually we call him KAJITA-san. Yeah. So KAJITA-san received his PhD from University of Tokyo in 1986 under the guidance of Nobel laureate Professor Toshiba. He is now the University Distinguished Professor of the University of Tokyo. And he was also the director of the Institute for Cosmic Ray Research from 2008 to 2022. He was also the director and the president of the Science Council of Japan between 2020 and 2023. I think this is a very important council advising the government for funding. Yeah. Now, regarding research, KAJITA-san has spent essentially his career at the Kamioka Observatory near Toyama since he was a graduate student. As a matter of fact, he is still utilizing this observatory. Now, of course, in the beginning, he focused on neutrino physics. He worked on the Kamioka Aokande, and also he was one of the few the founding member of the super Kamioka experiment. And then in 1998, at the Neutrino International Conference held at Takayama, Professor KAJITA then announced the discovery of atmospheric neutrino oscillation. And because of his very important role played in this discovery, he has received a lot of honors and also awards that I won't get into the details. Of course, the most important is he shared the 2015 Nobel Prize in physics. Now, after he wind down his research in neutrino physics, then he switched to gravitational wave, and he is the principal investigator of KAGRA, which is the topic of today's lecture. So let us welcome Professor KAJITA.
Okay, thank you very much for the kind introduction. Good afternoon. Well, today I want to talk about gravitational wave astronomy with KAGRA. KAGRA is a large-scale laser interferometer, and well, actually the image is shown here. It is located in underground, and of course, we'd like to observe something interesting happening in the universe. Okay, this is the outline of this talk. First, I have an introduction on gravitational waves. Then I want to move on to the KAGRA project. Of course, we'd like to contribute to the science. Therefore, I want to discuss about the gravitational wave astronomy and KAGRA. And before finishing, I want to mention about the future of the gravitational wave astronomy. Well, actually, I would say ground-based gravitational wave detectors. And I will summarize this talk. Okay, let's begin. Well, first, of course, when we talk about gravity, we cannot forget about Newton. Newton discovered the law of universal gravitation. And in fact, Newton's law explained various phenomena quite well, including the motion of the planets in the solar system. However, there were problems. In particular, I want to mention one thing. Well, although nothing can exceed the speed of light, but Newton's law of gravity implies that the force is transmitted instantaneously to the whole universe. So there's something wrong in principle. So therefore, in 1915, Albert Einstein discovered new law of gravity, the theory of general relativity. Then, in the subsequent year, Einstein predicted gravitational waves based on general relativity. So the idea of gravitational wave is more than 100 years old. Well, for example, if there are two black holes orbiting each other, then we expect strong gravitational waves. However, at the time of Einstein, he didn't know about black holes. Therefore, it is being told that Einstein thought that gravitational wave might be purely theoretical because the expected amplitude of the gravitational waves were extremely small. Anyway, let's talk about gravitational waves. Well, here in this slide, there are two black dots. They are black holes orbiting each other. Then, while orbiting each other, gravitational waves are emitted from this system. Therefore, these two black holes come closer and closer with time and orbiting faster and faster. Therefore, the gravitational wave frequency gets higher and higher. And, well, after some time, these two black holes come close, and then finally, these two black holes merge. And a new, heavier black hole is formed. So this is the expectation. And by the way, if we look at the outer space, you see that gravitational waves propagating to outside. So this is the expectation, well, theoretical expectation. And well, if there is a theory, of course, there should be people who would like to observe this theoretical prediction, gravitational wave. In fact, in 1960s, Joseph Weber constructed this kind of detector. And he tried to observe gravitational wave with this detector. And in fact, he had two detectors located in far apart locations. And then on one day, he recorded these two signals in two detectors. And he claimed the observation of gravitational waves. But, well, no one was able to re-observe similar signals. But, well, on the other hand, historically, I think this experiment motivated the detection of gravitational waves. Okay, that was in the 1960s. Then, in the 1970s, there was another idea. Well, I don't want to go into detail, but Ray Weiss proposed to use laser interferometer to observe gravitational waves. And in fact, this is the proposed laser interferometer by Ray Weiss in 1972. And well, okay, so I think this was the first serious consideration to observe gravitational waves with laser interferometers. By the way, how do we observe gravitational waves with laser interferometers? Well, okay, this is the image of the laser interferometer. Here's a laser, and here's the beam splitter. Half of the beam goes straight, and half of the beam is reflected to this direction. And then at the end of these two beams, there are mirrors. So then the coming back light have an interference. So, well, of course, laser light is a kind of wave, and therefore the coming back light merge and interfere, and typically the laser interferometer is tuned so that there is a minimum light here. But by some reason, if the mirror position changes, the interference pattern changes, and therefore we can see the change in the strength of the interference light. So this was the idea, quite simple. And indeed, on February 11th, 2016, there was an announcement of the discovery of gravitational wave by laser interferometers. And well, the person on this photo is Dave Reitze, LIGO Lab Executive Director, and he said, "Ladies and gentlemen, we have detected gravitational waves. We did it." Okay, well, okay, so what was the discovery? Well, there are actually two laser interferometers in the United States, and one is here, and another one is here. And these two detectors observed a quite similar signal. And well, after the observation on September 14th, 2015, LIGO team very carefully analyzed this data and concluded that LIGO observed the signals in their two laser interferometers. And the data told us that two black holes of 36 solar mass and 29 solar mass merged at a distance of 410 megaparsec, newly forming 62 solar mass black hole. So I think this was really a great discovery. The gravitational wave astronomy was born at that time. And indeed, as many of you may know, the 2017 Nobel Prize was awarded to these three people, Barry Barish, Kip Thorne, and Ray Weiss. By the way, usually people say Nobel Prize are typically awarded after, say, 20, 30 years. But the significance of this Nobel Prize is, well, announcement was 2016. Then the next year, the Nobel Prize was awarded to the observation of gravitational wave. So this tells us how important the gravitational wave observation is. Now, I want to talk about the more present status. Well, this is the map of the gravitational wave detectors. As I said, in United States, there are 2 LIGO interferometers, and in Europe, there is Virgo laser interferometer. And in Japan, we are working on the KAGRA laser interferometer. And in addition, we expect in the near future, there will be LIGO India laser interferometer. Well, I already told about the LIGO laser interferometer, but I want to say this is in fact a very large laser interferometer. Well, of course, from the photo, you see it's not a small scale facility. Indeed, it is a 4 kilometer by 4 kilometer laser interferometer. So it's really big. The Virgo laser interferometer is located in Italy, and it is also very big, 3 kilometer by 3 kilometer arm length. And these laser interferometers have already achieved high sensitivity and contributing to the gravitational wave observations. And this is the summary of LIGO Virgo observation before 2023. Here, the vertical axis is the mass of the stars, well, including black holes. In fact, blue circles show black holes, meaning, for example, in this case, 29 and 36 solar mass black holes merged, forming 62 solar mass black hole. So this is the summary of the observation before 2023. In total, LIGO and Virgo observed 90 events. And, well, you see, most of the circles are blue, and that means most of them are binary black hole mergers. But in addition, there are some orange circles in low mass region. They are neutron stars. So there are several binary neutron star mergers or neutron star black hole merger events. And I want to say, this is before 2023. Now, LIGO and Virgo are observing additional events, and much more events have been observed since 2023. So now, the frequency of the observation is rather high, maybe about 2 events per week. So you may feel that it is not so difficult to observe gravitational waves. I am not sure. Well, okay, let me tell you the sensitivity we need. Well, this is the sun and the earth. And if a gravitational wave comes to the solar system, of course, the distance between the sun and the earth changes. The question is, how much length change we expect for a strong gravitational wave that we can observe? Well, very simple answer is, if strong gravitational waves come to the solar system, the distance between the sun and the earth will change by about 10 to minus 8 centimeters. Therefore, every gravitational wave detector has to be sensitive to this length change. Well, you may think 10 to minus 8 centimeters length change could be not so difficult in the present day technology. Well, I think you are right. But the problem is we do not have laser interferometers with the arm length of 150 million kilometers. No, we don't have. We have only much smaller laser interferometers. The typical arm length is only 3 to 4 kilometers. Therefore, these detectors must be sensitive. Well, since the length is shorter, therefore, the effect of the gravitational wave is much smaller. Therefore, these detectors must be sensitive to the length change of 10 to minus 16 centimeters in 3 to 4 kilometers. Well, 10 to minus 16 centimeters is a very small number. Well, compared with the diameter of the proton, 10 to minus 16 is much, much, much smaller. So this tells us the detection of gravitational waves are not so simple. And in fact, well, in order to observe gravitational waves, we have to implement as many technologies as possible. Well, here I simply summarized what we need, the minimum things. But, well, today I don't have time. Therefore, I don't go into details. But let me tell just two things. Well, for example, if a mirror is put onto the ground, there's no way to observe gravitational waves. And therefore, these mirrors are kind of suspended. But in addition, it's very important to locate the laser interferometer in a seismic quiet place. And therefore, for example, in KAGRA, that I'm going to explain soon, we decided to put laser interferometer in underground. In addition, well, this is the image of a mirror. Of course, mirror is made of molecules, and molecules have the thermal motion. And this is going to be a problem. Well, due to the thermal motion, the surface of the mirror is, of course, not stable. This is a problem. Therefore, in case of KAGRA, we decided to cool down the mirror to the cryogenic temperature so that the thermal effect should be very small. Okay, now I want to move on to the KAGRA project. KAGRA is an international collaboration. Well, we have about 160 authors in KAGRA papers, and these authors come from these countries, and you find that most of these countries and regions are from the East Asian place. And again, this is the image of KAGRA. As I said, KAGRA is located underground to minimize the seismic noises. In addition, as I said, again, we use cryogenic mirrors to minimize the thermal noises. And we have been working on this project for about 15 years. By the way, I want to tell my personal history. As introduced at the beginning, I was a neutrino person, but now I'm working on gravitational waves. Why? Well, I studied neutrinos for more than 20 years. Well, 20 years is a long period. And after the discovery of neutrino oscillations in 1998, and after some more studies for several years, I was feeling that I finished what I should do in neutrino research. Of course, well, neutrino research itself is still very important, still very active, as we had this morning, for example. But I thought my contribution was finished. On the other hand, there are still many exciting science that we'd like to study. In particular, around 2005-6, the gravitational waves had not yet discovered at that time, and I was fascinated by the research on gravitational waves and the studies of the universe with gravitational waves. And in fact, in 2008, I became the director of the Institute for Cosmic Ray Research. And well, that was an important point. It was clear that I could no longer contribute to neutrino research much. But still, I wanted to be involved in exciting research. Therefore, I decided to participate in the gravitational wave project KAGRA with my partial time. Unfortunately, the KAGRA project was approved in 2010 by the Japanese government. So since then, I have been working on the KAGRA project. Okay, now I want to talk about the KAGRA project. First, the location. Well, it is located here. So in the mountain area in Japan. And well, okay, so this is a photo of the entrance to the KAGRA facility. Well, of course, it's in the mountain area. And in underground, we constructed the laser interferometer. And this photo shows a 3-kilometer long vacuum tube. Well, this photo is already pretty old, essentially 10 years ago. So, well, the first thing was the installation of this 3-kilometer long vacuum tube. Then we also needed to construct the central facility. And the central area looks like this. Unfortunately, the central area is covered by plastic. You cannot see very well what's going on. But, well, we need this kind of plastic system because we need extremely clean water. Clean, sorry. I used to be a neutrino physicist. Clean air to install the mirrors and so on. So everything in this plastic tent is extremely clean environment. And in fact, in this clean booth, we installed various systems, including the vibration isolation system. So you see a mirror here, and this mirror is suspended by a very complicated vibration isolation system. This is another one. Well, this is actually the biggest one. The whole system is about 14 meters high. And at the bottom, a mirror is suspended. And the mirror itself is like this. This photo was taken while we prepare the mirror. And this is actually going to be cooled down to 20 Kelvin. And, well, in fact, in order to cool down and achieve high sensitivity with the cryogenic temperature, we have to be very careful about the selection of the material. And this mirror material is actually sapphire, man-made sapphire, 23 kilogram. And after the preparation, this mirror come to the underground Kamioka to be installed in the vacuum. And well, essentially, it took us 10 years to finish the initial construction. And after finishing the initial construction in 2019, everyone were asked to go out underground, and everyone was asked to stay at the surface facility to do the commissioning to control the laser interferometer remotely. And well, also I want to mention that KAGRA, again, KAGRA is an international collaboration based largely on Asian countries and regions. We work together for the KAGRA project and for the gravitational wave astronomy. And this photo was taken in December 2024, that is last year. Well, due to COVID, for several years, it was not possible to have this kind of face-to-face collaboration meeting, but finally, people came back to discuss face-to-face. In addition, I want to mention one thing. Here in this page, I want to talk about the global gravitational wave network. I'm going to explain later a little bit more in detail, but to determine the location or direction of the gravitational wave source, we need at least 3 detectors which are located far apart from each other. Therefore, I think KAGRA is very important. Well, another 2 detectors are located in United States and Europe. So KAGRA should be in a very good position. And therefore, KAGRA joined the network observation with LIGO and Virgo. And in fact, we are working together. Namely, we observe gravitational waves simultaneously and analyze the data as a team. But, well, of course, we are behind compared with LIGO and Virgo. Therefore, our observation is still not very useful yet. Anyway, let me tell you the KAGRA project history between 2020 and 2023. After the 10 years of initial construction, in March 2020, KAGRA achieved the sensitivity of about 1 megaparsec, or about 3 million light years, and joined the gravitational wave network with LIGO and Virgo. But unfortunately, at that time, already COVID-19 pandemic was started, and it was impossible for people to come to the KAGRA site. Therefore, it was not possible for KAGRA to operate the laser interferometer for a long time. Therefore, we stopped the observation in 2 weeks. And then after that, we started the improvement work of the KAGRA laser interferometer. Then after a few years of improvement work during COVID-19, KAGRA rejoined the observation on May 24, 2023, with an improved sensitivity. But, well, to be honest, the sensitivity was still low. Therefore, we didn't think it's a good idea to continue observation for a long time. Therefore, KAGRA stopped the observation after 1 month of observation. and started the improvement work again. And we were hoping to rejoin the observation in the spring of 2024. Then, on January 1st, 2024, a magnitude 7.6 earthquake occurred at a distance of about 100 kilometers from the KAGRA site. And well, the epicenter was here, and these numbers show the seismic intensity based on Japanese seismic intensity scale, which is from 0 to 7. And 7 is really the strongest possible earthquake. And in fact, the earthquake was a local one, but a strong one. For example, the ground rose by 4 meters in some area of the Noto Peninsula. So this is the ground level change after the earthquake. Well, of course, the Hida city was 100 kilometers away. Therefore, the effect of the earthquake was not that big. But even in the Hida city, the land displacement was 2 to 4 centimeters. And at the surface KAGRA facility, well, things were like this. And well, this was the strongest earthquake in Hida city in the past 100 years. Okay, how about the KAGRA laser interferometer itself? Well, I think we were lucky because we constructed everything in underground. But still, KAGRA was damaged. Well, actually, in January last year, it was not possible to even enter into the underground because some earthquake activity continued. And KAGRA started the recovery work after 1 month from the big earthquake. And in October last year, KAGRA recovered to operate as a laser interferometer. And at present, KAGRA is trying to improve the sensitivity to about 10 megaparsec for binary neutron star mergers, which is an improvement nearly 1 order of magnitude compared with the previous ones. And we hope that KAGRA can join the observation in the spring of this year, finally. So this is really a very exciting time. And of course, well, achieving 10 megaparsec and join the observation is not the final goal. Of course, KAGRA will continue to improve the sensitivity to really contribute to the gravitational wave astronomy. Okay, so far I discussed what we have been doing, but well, I didn't talk about the KAGRA's contribution to the gravitational wave astronomy. So I want to talk about the gravitational wave astronomy with KAGRA. First, well, I would like to remind you that every laser interferometer has the direction that is very sensitive to the gravitational wave detection, but also there are some directions that are not so good for the gravitational wave detection. And in case of, for example, 2 LIGO interferometers, two LIGO interferometers, and these interferometers have very good sensitivity to these directions, but they do not have good sensitivity to these directions. And this is the case of Virgo, and this is the case of KAGRA. And you find KAGRA is complementary in the sensitivity direction to other detectors. And in fact, this is important. say, if we have LIGO and Virgo only, then the sensitivity map is like this. So compared with the single detector case, you find that high sensitivity region is much enhanced, but there are still several very low sensitivity directions. But if we have KAGRA in addition to LIGO and Virgo, then we find that these three project network has the sky coverage almost perfectly. In addition, I want to mention another thing. Well, okay. We'd like to observe a gravitational wave by these three detectors. And in fact, it's very important that there are at least three detectors located far from each other to determine the source direction or location accurately. If there are, say, LIGO and Virgo, then typically it is not possible to precisely pin down the direction. Instead, the allowed region is kind of line. But if we have one more detector, then we can pin down the direction. So therefore, we think KAGRA is very important. In fact, well, this is the gravitational wave signal observed in August 17, 2017. And this is the gravitational wave signal. Horizontal axis is time, and vertical axis is the frequency. And you see this is the observed signal. And this was the first observation of the merger of the binary neutron stars. And at that time, in addition to LIGO, Virgo was operating, and therefore these detectors constrain the direction of the signal to this accuracy. And then the telescopes found the optical counterpart. And therefore, after that, many telescopes tried to observe this object. And for example, one of the data are like this. Horizontal axis is days, and the vertical axis is the signal strength. And you see from ultraviolet to infrared, and depending on the frequency of these light, there is kind of light curves decaying. And this was just consistent with the formation or creation of heavy metals, such as gold or platinum. So we think this was really a great start of the real gravitational wave astronomy. And in fact, until that time, we are not sure how the gold or platinum were generated in the history of the universe. So at that moment, we began to know that binary neutron star mergers could be the main source of the heavy metals in the universe. So we think this is very important, and in fact, the collaboration of gravitational wave and optical telescopes are going to be very important. In addition, I want to say we need to collaborate with other people as well. For example, in order to understand what's going on with the merger of the binary neutron stars, it's very important to have a detailed simulation of the merger of these binary neutron stars. And here in this view graph, I'd like to show you one example of the calculation. Well, here's the, proton fraction, density, and magnetic field. And this is the large scale, and this is a small scale. And you see there are two neutron stars orbiting each other. And let me show you the movie. Okay, so after the merger, this is the simulation result. And look at this region, and here shows the formation of the heavy metals. The horizontal axis is number of neutrons, and the vertical axis is the number of protons. And well, after the merger, if we look at this region, you find that indeed, according to this simulation, heavy metals are generated. So this kind of simulation is very important to really interpret the data. By the way, this is actually not a simple simulation. According to this paper, they used 85 million CPU hours by Fugaku supercomputer. So this is really going to be, this is really very CPU intensive work. Anyway, we need to collaborate with these people. And of course, with these studies, we really want to understand, for example, the details of the neutron star mergers and how heavy metals in the universe were created. Now, let's move on to the next topic. That is the, okay, this one. This is the data, gravitational waves. And well, actually, essentially, I already explained. Blue ones are black holes. And well, actually, blue ones are the mergers of the binary black holes. In addition, here in this view graph, there are red circles. They are black holes observed by X-rays or electromagnetic observations. Then you immediately find that somehow blue ones are heavier than the red ones. Okay, I don't know. We do not know why this happened. Anyway, this may be quite interesting, and we would like to understand why gravitational waves observed so many heavier black holes. Well, okay, we have to continue to observe gravitational waves. But I think this is going to be a very important question we need to answer in the future observations. And finally, I would like to mention about other possibility. Well, of course, we know that at the end of the life of the heavy stars, there'll be a supernova explosion. Well, supernova explosion is not a very frequent event within our galaxy. But let's assume a supernova explodes within our galaxy, then we expect to observe gravitational waves, and at the same time, I'm sure there should be very significant neutrino data observed. And I believe by combining gravitational wave and neutrino data, we can truly understand the mechanism of the supernova explosion. Well, in fact, supernova explosion is another area where we need a very detailed simulation. And well, I don't know to what extent at present people are able to reproduce supernova explosion, but I believe we need data from gravitational waves and neutrinos and compared with the simulation result. So this kind of collaboration work among various scientific fields is very important. Okay, well, in the remaining 5 minutes or so, I want to very briefly discuss the future ground-based gravitational waves. Since the present generation of ground-based gravitational wave detectors have been so successful, there have been intense activities to design and propose the next generation detectors. There are two serious activities. One is Einstein telescope in Europe. Another one is the Cosmic Explorer in United States. And they are going to be very large scientific project. Well, for example, the baseline length would be, in this design, 10 kilometers for Einstein telescope and 40 kilometers in Cosmic Explorer. And KAGRA may contribute to this project by the experience of the underground site and the technology in the cryogenic mirrors. Anyway, in my opinion, these projects are really exciting. And I want to tell you why I am excited with these projects. This is the sensitivity of the future ground-based detectors. The horizontal axis is essentially the mass, and the vertical axis is the redshift. And these pink and green bands show the sensitivity of these Cosmic Explorer and Einstein telescope projects. And you find that these projects could be sensitive to the black hole mergers at a distance of redshift 100. Well, of course, at redshift 100, we do not expect any black hole mergers if all the black holes are created by normal stars, because normal stars, initial normal stars may not be created before redshift, I don't know, 20 or so. But, well, okay. There might be some signal, and if there is some signal in redshift 100, that could be quite interesting. So, well, I think the science with these future gravitational wave detectors will be really exciting. So, I think gravitational wave physics or astronomy will have a bright future. Okay, let me summarize. Gravitational wave was observed by LIGO thanks to the tremendous improvements in science and technology over the 100 years. So I would say mission impossible became possible. Gravitational wave astronomy is a new and exciting scientific field it will unveil the secrets of the universe. And KAGRA is a unique gravitational wave detector with cryogenic mirrors and the underground site. And as I discussed, KAGRA is recovering from the damage of the earthquake and would like to contribute to the gravitational wave astronomy as soon as possible. And we are really excited to start observations soon. Well, that's all what I wanted to say, and I hope I convinced you that gravitational wave astronomy is quite interesting and have a great future. And I hope young people doing gravitational wave in the future. Okay, that's all. Thank you very much.
Okay, thank you for a very interesting talk. So now we have the floor open for question. So any question?
Thank you for the nice lecture, Professor Kajita. I'm currently a neutrino student, and you convinced me that gravitational wave is very exciting. So I'm curious that is there any difference in technology between like KAGRA and LIGO, and what's the limiting factor of the current like KAGRA sensitivity, and how do you plan to improve it?
Thank you very much. Okay, there are two questions. One is the technology difference. In fact, KAGRA and LIGO are quite similar as far as the laser interferometer technology is concerned. But there are, well, as I mentioned, two differences. KAGRA was installed in underground to minimize the problem with the seismic activities. Also, KAGRA decided to use the cryogenic technology to reduce the problem related to the thermal effect. But anyway, as far as the design sensitivity is concerned, design sensitivity 15 years ago was concerned, we had quite similar sensitivity. But still, we are not achieving that high sensitivity because we need time. Well, okay. In these detectors, laser interferometers, we always have to struggle with noises. So, well, in operating the laser interferometer, we find some noise, then we try to remove them by improving the hardware. So we improve, then at the next level, there are some other noise coming out. So we have to find out the reason and try to remove by hardware improvement and so on. So this needs to continue for some time. And KAGRA is actually quite young. We still need time to achieve the design sensitivity. But we are working hard. And we are hoping that in a few years, we can achieve a reasonable sensitivity. May not be a design sensitivity, but a reasonably good sensitivity to really contribute to the gravitational wave of wave astronomy.
Okay, so let's see. Who has another question? Oh, over there. Okay. Yeah. No.
Or okay, now it's over.
Okay. Now, yes. Okay.
Okay. Yeah. Thanks, Professor Kajita again. Very inspiring talk. I'm already attracted to this new endeavor. Now, I try to limit myself to also two questions. One is about the impact of the earthquake. It's very impressive, fascinating to see how actually quick the experiment can recover within just a few months. And you mentioned also that it is planned underground. to reduce or to minimize the seismic effect. So the question is how low underground is it installed, and if you would do it again, like how much you would even go lower or something to avoid that.
Okay.
This is the first question.
Maybe let me answer to this question first. Well, actually, okay. I don't have the number, say, for example, the comparison of the acceleration at the surface and the underground. I don't have. But, well, okay, people told me at the surface, according to the Japanese seismic intensity scale, Hida City was 5-. But in underground, people told me that this number was 3. So, well, I cannot tell how much reduced, but this was a significant effect. And, well, usually, compared with the seismic activity at the surface, in underground, it is about 2 orders of magnitude reduced.
Okay. But do you have a number of like where it is installed, like compared to surface?
Well, okay. Well, KAGRA detector is typically located about 300 meters underground.
Okay, I see. Thanks. And then maybe just a very short question: is the interferometer plan like what is the lifetime planned for the interferometer? Is there a lifetime really, or you can keep improving?
Yeah, thank you. Well, since this is this was actually a very intense work to construct the detector. Therefore, we would like to operate the laser interferometer for a long time. And we have been saying to our funding agency that we'd like to continue observations for about 20 years.
Okay. So, another over there.
In view of the seismic vibration problem, and also the desire to have a longer baseline, will the next generation of a gravitational wave detector be built on 3 satellites on the solar orbit? So would there be advantage, and what would be the major technological challenge with that idea?
Thank you very much. In fact, 3 satellites at the space to form a laser interferometer is a very good idea. And in fact, a project is going on, essentially based in Europe. And this project is called LISA. And because of the, say, space, they do not worry about the length. And therefore, I think their baseline length is 2.5 million kilometers. So therefore, the LISA space gravitational wave antenna is sensitive to lower frequency gravitational waves. And in fact, in this sense, the ground-based laser interferometer and space laser interferometer are complementary. We think it's very important to have both.
Okay, over there.
Thank you very much, Kajita-san, again for this inspiring talk. I found this extremely interesting and also useful that as long as KAGRA is constructed, it's already bearing in mind the idea of forming a network of observation. So is there a plan to expand this collaboration, for example, to other possible or the future interferometers that you are saying? And also, is it possible to, for example, send alert to other observatories in, for example, electromagnetic in the optical band to form such cooperated observation?
Okay, thank you very much for this question. First of all, now, well, LIGO, Virgo, KAGRA are working together. On the other hand, we are still 3 independent collaborations. And we think it may not be a good way for a longer term. The decision making is a bit complicated. We are 3 independent groups. And therefore, at present, we are seriously discussing to form a single collaboration or consortium, I don't know, a single organization to work together even tightly. Then, of course, in the future, we may have new detectors. One example is the LIGO India. And we would like to, of course, we'd like to welcome them. But of course, the decision should be made by LIGO India collaboration. And even in the future, well, there should be Cosmic Explorer or Einstein Telescope. Of course, it will be beneficial if all of us work together. But well, we do not know what will happen. We hope things will go well. Now, about the alert to the electromagnetic community. Well, okay, I'm very sorry. I do not know the details of the present mechanism. I think there are pretty good information stream, but I'm very sorry. I don't know the details, sorry.
Yes, another question.
Good afternoon. Very, very inspiring talk. I'm not from physicist. I'm accelerator physicist guy. I'm engineer. And you see, in the accelerator now, we are planning for a very large infrastructure from LEP, and after we go to LHC, and now we want to do 100 kilometers. What do you think that it will be also a certain limit for you in doing bigger and bigger, or okay? And going to the cosmic is another thing, but is there anything that is telling to you, okay, there is a border for this and we could not go ahead? If you could, it could be very inspiring also for our community. And just to finish, I'm really happy that you have this global collaboration, that it could be an example also for the accelerator. Many thanks.
Well, okay, thank you very much. Well, okay, it's very difficult to predict the future, but well, physics-wise, if the next generation detectors, Cosmic Explorer and Einstein Telescope, if they are able to reach to the sensitivity of redshift 100, that is really amazing. And in fact, I am not sure if we have any motivation to improve the sensitivity further. I don't know. Maybe I'm too pessimistic. Well, of course, if we look at the data from these future detectors, we may find some new reason to construct even larger one. Let's see.
Okay. So any other question? Okay.
I would like to ask because I have noticed that you have mentioned in your talk that the KAGRA instrument is actually located inside the mine of Kamioka, which is in the proximity of Kamiokande neutrino detector. So my question is, how would the two instruments together, I mean, in more detail, that they would synergize the future research of supernova, and how could you possibly mitigate the effect of local noise sources?
Okay, thank you very much. Well, first of all, about the local noise source. Well, okay, certainly there should be local noise sources, but neutrinos and gravitational waves, the noises are completely different. So we do not worry about the common noise for these two detectors. Now, indeed, it is true that Super Kamiokande and KAGRA are located in the same mountain. And, well, as I mentioned very briefly, if we have a supernova within our galaxy, we really hope that these two detectors will give us very important information. And in particular, I want to say, because they are located in the same mountain, you do not need to worry about the correction in the propagation time. So the analysis should be it should be very easy. So therefore, this could be a synergy of the neutrino and gravitational wave.
Okay, thank you.
Okay. So, there's another question over there.
Thank you very much, Kajita-san. So I have a very naive question. So actually, I'm Japanese. I know that there are a lot of small earthquakes in Japan. I mean, almost every day, I think. Let's say if the, seismic interest scale 1 is almost every day, I guess. So then, I'm wondering if such a small earthquake could affect the, the KAGRA sensitivity. Maybe, yeah, it could be small enough, I guess. But yeah, could you give any comment on that?
Yeah, thank you for this question. In fact, small earthquakes are a problem for KAGRA. Well, sensitivity is not a problem. The problem is if a small earthquake happens, then we cannot operate the laser interferometer. Interferometer log will be down. So we lose some time, typically 1 hour or so. But if we have a little bit stronger one, then alignment is lost. Then we may need 1 week or so. So this is the problem. And well, we realize this is indeed a problem. Therefore, we are trying to improve the seismic isolation even further in the near future.
Okay, good. So, no more questions? Okay, so from this very the wonderful lecture, I think we have 2 take-homes messages. One is certainly gravitational wave is really exciting. That is one of our future. Now, there's the second take-home message, at least I got, is we can sell to the funding agency about gravitational wave because we can help them to locate tons of gold in space. Okay, let's thank the Kajita-san again.
Okay, thank you very much.